on the application of Laplace transformation in electric circuits. So at the end of this presentation, we should be able to apply solutions of Laplace transformation in electric circuits. So just like on the applications of electric circuits for first order differential equation, Laplace transformation can be used in solving such problems. So using Laplace transform as well as inverse Laplace transform. So we just have to recall that, for example, if we have a series RL circuit, so the voltage on the resistor so would be the product of the resistance times the current flowing on the circuit. And then if it is inductor, so the voltage across the inductor would be I multiplied it with the derivative of the current with respect to time. And using the KVL, so we will arrive to the equation to be Ri plus IDI over dt is equals to V. That is for series RL. And then for series RC circuit, so we could have the voltage across the resistance or across the resistor to be Ri, and the voltage across the capacitor, so which is 1 over C, the square root of I dt. But again, the integral of I dt is the same as Q. So therefore, so VC so could be equal to Q over C as well. And then from here, so if we will be deriving this, so Ri plus 1 over C, so we'll have R di over dt plus I all over C. So this one should be 0. Okay? So let's have an example. So involving an RL circuit, so which is shown below. So it has a voltage source of 5 volts, a resistance of 50 ohms, and an inductance of 1 Henry. So we are to find the current in the circuit at any time, so using Laplace transformation. So in doing so, using the formula for series, so we could apply the KVL. So it says that Ri is so plus L di over dt, so would be equal to V, or the voltage source. And in here, so we just need to substitute. So 50 I plus our inductance is 1 Henry. So that would just be di over dt. Then that would be equal to 5 volts. And rearranging our equation, so giving us di over dt, so plus 50I, and that would be equal to 5. And from here, so we could derive this one or transform this one using Laplace transformation. The Laplace transformation of the derivative. So let's say for I, so I'm just going to use the capital I. So that would be S, and then multiplied it with I of S, and then minus I of 0. That would be the for di over dt. So that is S I of S minus I of 0. And then we'll have plus 50 I of S, so for just I. And then that would be equal to the Laplace transform of 5, so which is 5 over S. However, based from the problem, it says that there is no initial current. So therefore, I of 0 is equals to 0. So that's canceling that out. So giving us factoring I of s, so that would give us s plus 50. So multiplied it with I of s, then 5 over s. So getting I of s, that would be 5 over s times s plus 50. And from here, so to determine, so this current I of s, we will be getting the inverse Laplace of this given function, and then from there, to do that, so we need to find the partial decomposition. So for 5 over s times s plus 50, that would be a all over s, then plus b all over s plus 50. So 5 then would be equal to a times s plus 50 plus b times s. Okay, so when to get the value of a, so when s is equals to 0, so we'll have 5 is equals to a times 50. And therefore a is equals to 5 over 50, which is 1 all over 10. And then when s is negative 50, so when s is negative 50, so 5 is equals to negative 50, the a would be 0, so b times negative 50. So a then would just be equal to negative 1 over 10. Okay, so for our b. So therefore, our I of s then, so would be 1 over 10, so divide it with s, and then plus, minus 1 over 10 over s plus 50. And from here, we will be getting I of t. So I of t is the inverse Laplace. So I of t then, so would just be 1 over 10, then the inverse Laplace of 1 over s. And then we'll have minus 1 over 10, and the inverse Laplace of 1 over s plus 50. Or simply put, I of t will be then equivalent to 1 over 10. Inverse Laplace of 1 over s is just 1. Then minus 1 over 10 e raised to, so this is exponential, so negative 50t. And this would be the current at any time t, so for the given circuit. So 1 over 10 minus 1 over 10 e raised to negative 50t. Okay, so that's the current at any time t for this given RL circuit. So let's have another example. So this time around, it would be an RC circuit, and then we are to find what would be the voltage across the capacitor at any instant of time. So given that the voltage source is 100 volts, the resistance would be 5 ohms, and then we have a capacitance of 0.002 farad, or the 20 millifarad. Okay. And again, so initially there is no charge on the circuit. So using KVL, so we have an RI, then plus 1 over C, and then I could just use Q here. Right? So Q over C is equals to V. However, I is dq over dt, then plus q all over c then, so would be equal to V. So substituting our given, so we have a resistance of 5 ohms, so that would be 5 dq over dt, and then our C is 0.02, so Q over 0.02, and that would be equal to 100. So 5 dq over dt, so plus 1 divided with 0.02, so we'll have 50 q, and that would be equal to 100. So if we want to simplify this further, so dq over dt, so plus 50 divides 5 is 10q, is equals to 20. So dq over dt plus 10q is equals to 20. So we can now solve this one. So using our Laplace transformation, so this would be S. I'm just going to use Q of t, and minus Q of 0, and then plus 10 Q of t is equals to 20 all over S. Next, so we'll have initially there's no charge, so Q of 0 is equals to 0, so therefore that would cancel out, and we could factor out, so we'll have S plus 10 then, and Q of t is equals to 20 over S. So Q of t then, so would be equal to 20 all over S times S plus 10. And applying partial fraction, so we'll have 20 over S times S plus 10, so equal to A all over S plus B all over S plus 10. So 20 then would be equal to A S plus 10, then plus B times S. So finding the value of A, so that is when S is equal to 0, so we'll have 20 is equals to A times 10. So A then is equals to 2. And then when S is equals to negative 10, so 20, so negative 10 times 0, or negative B times negative 10. So B then would be equal to negative 2. So from here, so we have Q of t, so to be equivalent to 2 over S, then minus 2 all over S plus 10. This should be Q of S. So this is Q of S. And then our Q of S is 2 over S minus 2 over S plus 10. So Q of t this time around, so would be 2, then the Laplace and inverse Laplace of 1 over S, then minus 2, the inverse Laplace of 1 over S plus 10. So Q of t then would be equivalent to 2 minus 2 e raised to negative 10 t. And that would be the charge at any time. So the voltage across the capacitor at any time, so would be Q of t divided with C, or 2 minus 2 e raised to negative 10t, so divided with 0.02. So our voltage across the capacitor at any time would be 100 minus 100 e raised to negative 10t. And that is the voltage across the capacitor at any time t. So that's all for this application. Thank you.